Fuel management in multi-engine airplanes is often more complex than in single-engine airplanes. Depending upon system design, the pilot may need to select between main tanks and auxiliary tanks or even employ fuel transfer from one tank to another. In complex fuel systems, limitations are often found restricting the use of some tanks to level flight only or requiring a reserve of fuel in the main tanks for descent and landing. Electric fuel pump operation can also vary widely among different models, particularly during tank switching or fuel transfer. Some fuel pumps are to be on for takeoff and landing, others are to be off. There is simply no substitute for thorough systems and AFM/POH knowledge when operating complex aircraft. Slow flight. There is nothing unusual about maneuvering during slow flight in a multi-engine airplane. Slow flight may be conducted in straight and level flight, turns, climbs, or descents. It can also be conducted in the clean configuration, landing configuration, or at any other combination of landing gear and flaps. Slow flight in a multi-engine airplane should be conducted so the maneuver can be completed no lower than 3,000 feet AGL or higher if recommended by the manufacturer. In all cases, practicing slow flight should be conducted at an adequate height above the ground for recovery should the airplane inadvertently stall. Pilots should closely monitor cylinder head and oil temperatures during slow flight. Some high-performance multi-engine airplanes tend to heat up fairly quickly under some conditions of slow flight, particularly in the landing configuration. Simulated engine failures should not be conducted during slow flight. The airplane will be well below VSSE and very close to VMC. Stability, stall warning, or stall avoidance devices should not be disabled while maneuvering during slow flight. Spin awareness in stalls. No multi-engine airplane is approved for spins, and their spin recovery characteristics are generally very poor. It is therefore prudent to practice spin avoidance and maintain a high awareness of situations that can result in an inadvertent spin. Spin awareness. In order to spin any airplane, a stalled condition needs to exist. At the stall, the presence or introduction of a yawing moment can initiate spin entry. In a multi-engine airplane, the yawing moment may be generated by rudder input or asymmetrical thrust. It follows, then, that spin awareness be at its greatest during VMC demonstrations, stall practice, slow flight, or any condition of high asymmetrical thrust, particularly at low speed/high AOA. Single-engine stalls are not part of any multi-engine training curriculum. No engine failure should ever be introduced below safe, intentional one-engine inoperative speed, VSSE. If no VSSE is published, use VYSE. Other than training situations, the multi-engine airplane is only operated below VSSE for mere seconds just after liftoff or during the last few dozen feet of altitude in preparation for landing. For spin avoidance when practicing engine failures, the flight instructor should pay strict attention to the maintenance of proper airspeed and bank angle as the learner executes the appropriate procedure. The instructor should also be particularly alert during stall and slow flight practice. While flying with a center of gravity closer to the forward limit provides better stall and spin avoidance characteristics, it does not eliminate the hazard. When performing a VMC demonstration, the instructor should also be alert for any sign of an impending stall. The learner may be highly focused on the directional control aspect of the maneuver to the extent that impending stall indications go unnoticed. If a VMC demonstration cannot be accomplished under existing conditions of density altitude, the instructor may, for training purposes, utilize a rudder blocking technique. As very few twins have ever been spin tested, none are required to. The recommended spin recovery techniques are based only on the best information available. The departure from controlled flight may be quite abrupt and possibly disorienting. The direction of an upright spin can be confirmed from the turn needle or the symbolic airplane of the turn coordinator, if necessary. Do not rely on the ball position or other instruments. If a spin is entered, most manufacturers recommend immediately retarding both throttles to idle, applying full rudder opposite the direction of rotation, and applying full forward elevator/stabilator pressure, with ailerons neutral. These actions should be taken as near simultaneously as possible. The control should then be held in that position until the spin has stopped. At that point, adjust rudder pressure, back elevator pressure, and power as necessary to return to the desired flight path. Pilots should be aware that a spin recovery will take considerable altitude, therefore, it is critical that corrective action be taken immediately. Stall training. It is recommended that stalls be practiced at an altitude that allows recovery no lower than 3,000 feet AGL for multi-engine airplanes, or higher if recommended by the AFM/POH. Losing altitude during recovery from a stall is to be expected. End of page 13 to 18. Stall characteristics vary among multi-engine airplanes just as they do with single-engine airplanes, and therefore, a pilot should be familiar with them. Yet, the most important stall recovery step in a multi-engine airplane is the same as it is in all airplanes: reduce the angle of attack, AOA. For reference, the stall recovery procedure described in Chapter 5 is included in Figure 13.9. Following a reduction in the AOA and the stall warning being eliminated, the wings should be rolled level and power added as needed. Immediate full application of power in a stalled condition has an associated risk due to the possibility of asymmetric thrust. In addition, single-engine stalls, or stalls with significantly more power on one engine than the other, should not be attempted due to the likelihood of a departure from controlled flight and possible spin entry. Similarly, simulated engine failures should not be performed during stall entry and recovery. Power-off approach to stall, approach and landing. A power-off approach to stall is trained and checked to simulate problematic approach and landing scenarios. A power-off approach to stall may be performed with wings level, or from shallow turns, up to 20 degrees of bank. To initiate a power-off approach to stall maneuver, the area surrounding the airplane should first be cleared for possible traffic. The airplane should then be slowed and configured for an approach and landing. A stabilized descent should be established, approximately 500 fpm, and trim adjusted. A turn should be initiated at this point, if desired. The pilot should then smoothly increase the AOA to induce a stall warning. Power is reduced further during this phase, and trimming should cease at speeds slower than takeoff. When the airplane reaches the stall warning, e.g., oral alert, buffet, etc., the recovery is accomplished by first reducing the AOA until the stall warning is eliminated. The pilot then rolls the wings level with coordinated use of the rudder and smoothly applies power as required. The airplane should be accelerated to Vx if simulated obstacles are present, or Vy during recovery and climb. Considerable forward elevator/stabilator pressure will be required after the stall recovery as the airplane accelerates to Vx or Vy. Appropriate trim input should be anticipated. The flap setting should be reduced from full to approach, or as recommended by the manufacturer. Then, with a positive rate of climb, the landing gear is selected up. The remaining flaps are then retracted as a positive rate of climb continues. Power-on approach to stall, takeoff and departure. A power-on approach to stall is trained and checked to simulate problematic takeoff scenarios. A power-on approach to stall may be performed from straight and level flight or from shallow and medium bank turns, up to 20 degrees of bank. To initiate a power-on approach to stall maneuver, the area surrounding the airplane should always be cleared to look for potential traffic. The airplane is slowed to the manufacturer's recommended liftoff speed. The airplane should be configured in the takeoff configuration. Trim should be adjusted for this speed. Engine power is then increased to that recommended in the AFM/POH for the practice of power-on approach to stall. In the absence of a recommended setting, use approximately 65% of maximum available power. Begin a turn, if desired, while increasing AOA to induce a stall warning, e.g., oral alert, buffet, etc. Other specified, reduced, power settings may be used to simulate performance at higher gross weights and density altitudes. When the airplane reaches the stall warning, the recovery is made first by reducing the AOA until the stall warning is eliminated. The pilot then rolls the wings level with coordinated use of the rudder and applying power as needed. However, if simulating limited power available for high gross weight and density altitude situations, the power during the recovery should be limited to that specified. The landing gear should be retracted when a positive rate of climb is attained, and flaps retracted, if flaps were set for takeoff. The target airspeed on recovery is Vx if, simulated, obstructions are present, or Vy. The pilot should anticipate the need for nose-down trim as the airplane accelerates to Vx or Vy after recovery. End of page 13 to 19. Full stall. It is not recommended that full stalls be practiced unless a qualified flight instructor is present. A power-off or power-on full stall should only be practiced in a structured lesson with clear learning objectives and cautions discussed. The goals of the training are: A. To provide the pilots the experience of the handling characteristics and dynamic cues, e.g., buffet, roll-off, near and at full stall end. B. To reinforce the proper application of the stall recovery procedures. Given the associated risk of asymmetric thrust at high angles of attack and low rudder effectiveness due to low airspeeds, this reinforces the primary step of first lowering the AOA, which allows all control surfaces to become more effective and allows for roll to be better controlled. Thrust should only be used as needed in the recovery. Accelerated approach to stall. Accelerated approach to stall should be performed with a bank of approximately 45 degrees, and in no case at a speed greater than the airplane manufacturer's recommended airspeed, the specified design maneuvering speed, VA, or operating maneuvering speed, VO. The pilot should select an entry altitude that will allow completion of the maneuver no lower than 3,000 feet AGL. The entry method for the maneuver is no different than for a single-engine airplane. Once at an appropriate speed, begin increasing the back pressure on the elevator while maintaining a coordinated 45 degrees turn. A good speed reduction rate is approximately 3 to 5 knots per second. Once a stall warning occurs, recover promptly by reducing the AOA until the stall warning stops. Then, roll the wings level with coordinated rudder and add power as necessary to return to the desired flight path. Normal approach and landing. Given the higher cruising speed, and frequently altitude, of multi-engine airplanes over most single-engine airplanes, the descent needs to be planned in advance. A hurried, last-minute descent with power at or near idle is inefficient and can cause excessive engine cooling. It may also lead to passenger discomfort, particularly if the airplane is unpressurized. As a rule of thumb, if terrain and passenger conditions permit, a maximum of a 500 fpm rate of descent should be planned. Pressurized airplanes can plan for higher descent rates if desired. In a descent, some airplanes require a minimum EGT or may have a minimum power setting or cylinder head temperature to maintain. In any case, combinations of very low manifold pressure and high RPM settings are strongly discouraged by engine manufacturers. If higher descent rates are necessary, the pilot should consider extending partial flaps or lowering the landing gear before retarding the power excessively. The descent checklist should be initiated upon leaving cruising altitude and completed before arrival in the terminal area. Upon arrival in the terminal area, pilots are encouraged to turn on their landing and recognition lights when operating below 10,000 feet, day or night, and especially when operating within 10 miles of any airport or in conditions of reduced visibility. The traffic pattern and approach are typically flown at somewhat higher indicated airspeeds in a multi-engine airplane contrasted to most single-engine airplanes. The pilot may allow for this through an early start on the before-landing checklist. This provides time for proper planning, spacing, and thinking well ahead of the airplane. Many multi-engine airplanes have partial flap extension speeds above VFE, and partial flaps can be deployed prior to traffic pattern entry. Normally, the landing gear should be selected and confirmed down when abeam the intended point of landing as the downwind leg is flown. Figure 13.10. The FAA recommends a stabilized approach concept. To the greatest extent practical, on final approach and within 500 feet AGL, the airplane should be on speed, in trim, configured for landing, tracking the extended centerline of the runway, and established in a constant angle of descent toward an aim point in the touchdown zone. Absent unusual flight conditions, only minor corrections are required to maintain this approach to the roundout and touchdown. The final approach should be made with power and at a speed recommended by the manufacturer. If a recommended speed is not furnished, the speed should be no slower than the single-engine best rate of climb speed, VYSA, until short final with the landing assured, but in no case less than critical engine out minimum control speed, VMC. Some multi-engine pilots prefer to delay full flap extension to short final with the landing assured. This is an acceptable technique with appropriate experience and familiarity with the airplane. In the roundout for landing, residual power is gradually reduced to idle. With the higher wing loading of multi-engine airplanes and with the drag from two windmilling propellers, there is minimal float. Full stall landings are generally undesirable in twins. The airplane should be held off as with a high-performance single-engine model, allowing touchdown of the main wheels prior to a full stall. End of page 13 to 20. Under favorable wind and runway conditions, the nosewheel can be held off for best aerodynamic braking. Even as the nosewheel is gently lowered to the runway centerline, continued elevator back pressure greatly assists the wheel brakes in stopping the airplane. If runway length is critical, or with a strong crosswind, or if the surface is contaminated with water, ice, or snow, it is undesirable to rely solely on aerodynamic braking after touchdown. The full weight of the airplane should be placed on the wheels as soon as practicable. The wheel brakes are more effective than aerodynamic braking alone in decelerating the airplane. Once on the ground, elevator back pressure should be used to place additional weight on the main wheels. When necessary, wing flap retraction also adds additional weight to the wheels and improves braking effectivity. Flap retraction during the landing rollout is discouraged, however, unless there is a clear, operational need. It should not be accomplished as routine with each landing. Some multi-engine airplanes, particularly those of the cabin class variety, can be flown through the round out in touchdown with a small amount of power. This is an acceptable technique to prevent high sink rates and to cushion the touchdown. The pilot should keep in mind, however, that the primary purpose in landing is to get the airplane down and stopped. This technique should only be attempted when there is a generous margin of runway length. As propeller blast flows directly over the wings, lift as well as thrust is produced. The pilot should taxi clear of the runway as soon as speed and safety permit, and then accomplish the after-landing checklist. Ordinarily, no attempt should be made to retract the wing flaps or perform other checklist duties until the airplane has been brought to a halt when clear of the active runway. Exceptions to this would be the rare operational needs discussed above, to relieve the weight from the wings and place it on the wheels. In these cases, AFM/POH guidance should be followed. The pilot should not indiscriminately reach out for any switch or control on landing rollout. An inadvertent landing gear retraction while meaning to retract the wing flaps may result. Crosswind approach and landing. The multi-engine airplane is often easier to land in a crosswind than a single-engine airplane due to its higher approach and landing speed. In any event, the principles are no different between singles and twins. Prior to touchdown, the longitudinal axis should be aligned with the runway centerline to avoid landing gear side loads. The two primary methods, crab and wing low, are typically used in conjunction with each other. As soon as the airplane rolls out onto final approach, the crab angle to track the extended runway centerline is established. This is coordinated flight with adjustments to heading to compensate for wind drift either left or right. Prior to touchdown, the transition to a side slip is made with the upwind wing lowered and opposite rudder applied to prevent a turn. The airplane touches down on the landing gear of the upwind wing first, followed by that of the downwind wing, and then the nose gear. Follow-through with the flight controls involves an increasing application of aileron into the wind until full control deflection is reached. End of page 13 to 21. The point at which the transition from the crab to the side slip is made is dependent upon pilot familiarity with the airplane and experience. With high skill and experience levels, the transition can be made during the round out just before touchdown. With lesser skill and experience levels, the transition is made at increasing distances from the runway. Some multi-engine airplanes, as some single-engine airplanes, have AFM/POH. Limitations against slips in excess of a certain time period, 30 seconds, for example. This is to prevent engine power loss from fuel starvation as the fuel in the tank of the lowered wing flows toward the wingtip, away from the fuel pickup point. This time limit should be observed if the wing-low method is utilized. Some multi-engine pilots prefer to use differential power to assist in crosswind landings. The asymmetrical thrust produces a yawing moment little different from that produced by the rudder. When the upwind wing is lowered, power on the upwind engine is increased to prevent the airplane from turning. This alternate technique is completely acceptable, but most pilots feel they can react to changing wind conditions quicker with rudder and aileron than throttle movement. This is especially true with turbocharged engines where the throttle response may lag momentarily. The differential power technique should be practiced with an instructor before being attempted alone. Short field approach and landing. The primary elements of a short field approach and landing do not differ significantly from a normal approach and landing. Many manufacturers do not publish short field landing techniques or performance charts in the AFM/POH. In the absence of specific short field approach and landing procedures, the airplane should be operated as recommended in the AFM/POH. No operation should be conducted contrary to the AFM/POH recommendations. The emphasis in a short-field approach is on configuration, full flaps, a stabilized approach with a constant angle of descent, and precise airspeed control. As part of a short-field approach and landing procedure, some AFM/POHs recommend a slightly slower than normal approach airspeed. If no such slower speed is published, use the AFM/POH recommended normal approach speed. Full flaps are used to provide the steepest approach angle. If obstacles are present, the approach should be planned so that no drastic power reductions are required after they are cleared. The power should be smoothly reduced to idle in the round-out prior to touchdown. Pilots should keep in mind that the propeller blast blows over the wings, providing some lift in addition to thrust. Reducing power significantly just after obstacle clearance usually results in a sudden, high sink rate that may lead to a hard landing. After the short-field touchdown, maximum stopping effort is achieved by retracting the wing flaps, adding back pressure to the elevator/stabilator, and applying heavy braking. However, if the runway length permits, the wing flaps should be left in the extended position until the airplane has been stopped clear of the runway. There is always a significant risk of retracting the landing gear instead of the wing flaps when flap retraction is attempted on the landing rollout. Landing conditions that involve a short field, high winds, or strong crosswinds are just about the only situations where flap retraction on the landing rollout should be considered. When there is an operational need to retract the flaps just after touchdown, it needs to be done deliberately with the flap handle positively identified before it is moved. Go around. When the decision to go around is made, the throttle should be advanced to takeoff power and pitch adjusted to arrest the sink rate. With adequate airspeed, the airplane should be placed in a climb pitch attitude. These actions, which are accomplished sequentially, arrest the sink rate and place the airplane in the proper attitude for transition to a climb. The initial target airspeed is Vy or Vx if obstructions are present. With sufficient airspeed, the flaps should be retracted from full to an intermediate position and the landing gear retracted when there is a positive rate of climb and no chance of runway contact. The remaining flaps should then be retracted. Figure 13:11. End of page 13 to 22. If the go-around was initiated due to conflicting traffic on the ground or aloft, the pilot should consider maneuvering to the side to keep the conflicting traffic in sight. This may involve a slight turn to offset from the runway/landing area. If the airplane was in trim for the landing approach when the go-around was commenced, it soon requires a great deal of forward elevator/stabilator pressure as the airplane accelerates away in a climb. The pilot should apply appropriate forward pressure to maintain the desired pitch attitude. Trim should be commenced immediately. The balked landing checklist should be reviewed as workload permits. Flaps should be retracted before the landing gear for two reasons. First, on most airplanes, full flaps produce more drag than the extended landing gear. Secondly, the airplane tends to settle somewhat with flap retraction, and the landing gear should be down in the event of an inadvertent, momentary touchdown. Many multi-engine airplanes have a landing gear retraction speed significantly less than the extension speed. Care should be exercised during the go-around not to exceed the retraction speed. If the pilot desires to return for a landing, it is essential to re-accomplish the entire before landing checklist. An interruption to a pilot's habit patterns, such as a go-around, is a classic scenario for a subsequent gear-up landing. The preceding discussion about performing a go-around assumes that the maneuver was initiated from normal approach speeds or faster. If the go-around was initiated from a low airspeed, the initial pitch up to a climb attitude should be tempered with the necessity to maintain adequate flying speed throughout the maneuver. Examples of where this applies include a go-around initiated from the landing round-out or recovery from a bad bounce, as well as a go-around initiated due to an inadvertent approach to a stall. The first priority is always to maintain control and obtain adequate flying speed. A few moments of level or near-level flight may be required as the airplane accelerates up to climb speed. Engine inoperative flight principles. There are two main considerations for OEI operations: performance and control. Multi-engine pilots learn to operate the airplane for maximum rate of climb performance at the blue radial indicated airspeed by training to fly without sideslip. Pilots also learn to recognize and recover from loss of directional control associated with the red radial indicated airspeed by performing a VMC demonstration. Since the object of a VMC demonstration is not performance, sideslip occurs during the maneuver. Detailed discussion on both the loss of directional control and maximum OEI climb performance follows. Derivation of VMC. VMC is a speed established by the manufacturer, published in the AFM/POH, and marked on most airspeed indicators with a red radial line. A knowledgeable and competent multi-engine pilot understands that VMC is not a fixed airspeed under all conditions. VMC is a fixed airspeed only for the very specific set of circumstances under which it was determined during aircraft certification. In reality, VMC varies with a variety of factors as outlined below. The VMC noted in practice and demonstration, or in actual OEI operation, could be less or even greater than the published value, depending on conditions and pilot technique. Historically, in aircraft certification, VMC is the sea-level calibrated airspeed at which, when the critical engine is suddenly made inoperative, it is possible to maintain control of the airplane with that engine still inoperative and then maintain straight flight at the same speed with an angle of bank not more than 5 degrees. The foregoing refers to the determination of VMC under dynamic conditions. This technique is only used by highly experienced test pilots during aircraft certification. It is unsafe to be attempted outside of these circumstances. In aircraft certification, there is also a determination of VMC under static or steady-state conditions. If there is a difference between the dynamic and static speeds, the higher of the two is published as VMC. The static determination is simply the ability to maintain straight flight at VMC with a bank angle of not more than 5 degrees. This more closely resembles the VMC demonstration task in the practical test for a multi-engine rating. The AFM/PO published VMC is determined with the critical engine inoperative. The critical engine is the engine whose failure had the most adverse effect on directional control. On twins with each engine rotating in conventional, clockwise rotation as viewed from the pilot's seat, the critical engine will be the left engine. Multi-engine airplanes are subject to P-factor just as single-engine airplanes are. The descending propeller blade of each engine will produce greater thrust than the ascending blade when the airplane is operated under power and at positive angles of attack. The descending propeller blade of the right engine is also a greater distance from the center of gravity, and therefore has a longer moment arm than the descending propeller blade of the left engine. As a result, failure of the left engine will result in the most asymmetrical thrust, adverse yaw, as the right engine will be providing the remaining thrust. Figure 13.12. End of page 13 to 23. Many twins are designed with a counter-rotating right engine. With this design, the degree of asymmetrical thrust is the same with either engine inoperative. No engine is more critical than the other, and a VMC demonstration may be performed with either engine windmilling. The following bullets describe the way several factors affect VMC speed for those multi-engine airplanes often used during training, which were certified in accordance with historical 14 CFR Part 23, Section 23.149. They also describe the conditions used to determine the manufacturer's published speed. Historically, in aircraft certification, dynamic VMC has been determined under the following conditions outlined in historical 14 CFR Part 23, Section 23.149. 1. Maximum available takeoff power initially on each engine, Section 23.149, B.1. VMC increases as power is increased on the operating engine. With normally aspirated engines, VMC is highest at takeoff power and sea level, and decreases with altitude. With turbocharged engines, takeoff power, and therefore VMC, remains constant with increases in altitude up to the engine's critical altitude, the altitude where the engine can no longer maintain 100% power. Above the critical altitude, VMC decreases just as it would with a normally aspirated engine whose critical altitude is sea level. In order to avoid accidents, test pilots conduct VMC tests at a variety of altitudes, and the results of those tests are then extrapolated to a single, sea level value. 2. All propeller controls in the recommended takeoff position throughout VMC determination, Section 23.149, B.5. VMC increases with increased drag on the inoperative engine. VMC is highest, therefore, when the critical engine propeller is windmilling at the low pitch, high RPM blade angle. VMC is normally determined with the critical engine propeller windmilling in the takeoff position, unless the engine is equipped with an autofeather system. 3. Most unfavorable weight and center of gravity position, section 23.149b. VMC increases as the center of gravity, CG, is moved aft. The moment arm of the rudder is reduced, and therefore its effectivity is reduced, as the CG is moved aft. For a typical light twin, the aftmost CG limit is the most unfavorable CG position. Historically, 14 CFR Part 23 calls for VMC to be determined at the most unfavorable weight. For twins certificated under CAR3 or early 14 CFR Part 23, the weight at which VMC was determined was not specified. VMC increases as weight is reduced. Figure 13. End of page 13 to 24. 4. Landing gear retracted, section 23.149b, 4. VMC increases when the landing gear is retracted. Extended landing gear aids directional stability, which tends to decrease VMC. 5. E-flaps in the takeoff position, section 23.149b, 3. This normally includes wing flaps and cowl flaps. For most twins, this will be 0 degrees of flaps. 6. Airplane trimmed for takeoff, section 23.149b, 2. 7. Airplane airborne and the ground effect negligible, section 23.149b. 8. Maximum of 5 degrees angle of bank, section 23.149a. VMC is highly sensitive to bank angle. To prevent claims of an unrealistically low VMC speed in aircraft certification, the manufacturer is permitted to use a maximum of a 5 degrees bank angle toward the operative engine. The horizontal component of lift generated by the bank balances the side force from the rudder, rather than using sideslip to do so. Sideslip requires more rudder deflection, which in turn increases VMC. The bank angle works in the manufacturer's favor in lowering VMC since using high bank angles reduces required rudder deflection. However, this method may result in unsafe flight from both the large sideslip and the need to increase the angle of attack in order to maintain the vertical component of lift. VMC increases as bank angle decreases. In fact, VMC may increase more than 3 knots for each degree of bank reduction between 5 degrees and wings level. Since VMC was determined with up to 5 degrees of bank, loss of directional control may be experienced at speeds almost 20 knots above published VMC when the wings are held level. The 5 degrees bank angle maximum is a historical limit imposed upon manufacturers in aircraft certification. The 5 degrees bank does not inherently establish zero sideslip or best single-engine climb performance. Zero sideslip, and therefore best single-engine climb performance, may occur at bank angles less than 5 degrees. The determination of VMC in certification is solely concerned with the minimum speed for directional control under a very specific set of circumstances, and not the optimum airplane attitude or configuration for climb performance. During dynamic VMC determination in aircraft certification, cuts of the critical engine using the mixture control are performed by flight test pilots while gradually reducing the speed with each attempt. VMC is the minimum speed at which directional control could be maintained within 20 degrees of the original entry heading when a cut of the critical engine was made. During such tests, the climb angle with both engines operating was high, and the pitch attitude following the engine cut had to be quickly lowered to regain the initial speed. Transitioning pilots should understand that attempting to demonstrate VMC with an engine cut from high power, or intentionally failing an engine at speeds less than VSSE creates a high likelihood for loss of control and an accident. End of page 13 to 25.